Okay, let's talk about scatterplot, correlation, and regression again. Here are the top 10 steel roller coasters in the world, according to a 2013 internet poll. That's the latest poll I could get my hands on. Their duration in seconds and length in feet. Okay, duration in seconds, lengths in feet. I haven't been on any of these. Instead, my kids and I have gone on the rides at Six Flags Great America. Calculate the correlation and the coefficient of determination. That is, the correlation between the duration and the length. Using SPSS, Excel, or TI, we find that the correlation is r equals 0.717, and the coefficient of determination is r squared, 0.514. Now, the coefficient of determination is 0.514, which is sizable. Can we conclude that a linear model is appropriate for these data? No, you have to look at the scatter plot. For example, the data in this scatter plot from an earlier problem also has a large coefficient of determination, 0.927, but a linear model is not appropriate. So again, you can see that these data do not fit a linear model, even though the correlation is pretty good. So even with a coefficient of determination of 0.927, you can conclude that a linear model is appropriate. Well, let's produce a scatter plot of the roller coaster data and see if it really does fit a linear model. Here's what the scatter plot looks like. Duration versus length. Yeah, that looks more or less linear. I think that's close enough to a linear model. Find the equation of the least squares regression line, also called the best fit line, and graph the least squares regression line on the scatter plot. Okay, using SPSS, Excel, or even a TI, we find that the least squares regression line is y hat equals 15.46x plus 2252. Again, recall that we use y hat with a least squares regression line. Y hat is the predicted value of y. And here's the scatter plot with the line. For the least squares regression line, y hat equals 15.46x plus 2252, give a physical interpretation of the slope and state the units for the slope. The slope of any line is change in y over change in x. The least squares regression line, y hat equals 15.46x plus 2252, has slope 15.46, because that's the coefficient of x. This means that if the duration x increases by 1 second, we'd predict that length would increase by 15.46 feet. Again, because slope is change in y over change in x. And if x changes by 1, y will change by 15.46. The units in this case are feet per second. Now be careful. We say that the units are feet per second, but that's not speed. We don't say feet per second because that's the speed it's traveling. We're not saying that the roller coaster travels 15.46 feet per second. Instead, it's feet of length over seconds in duration. So that's what we mean by feet per second. Plot the residuals. Okay, here's another way to see if we have a linear model. Yeah, the residuals, yeah, that's what you want to see with residuals. That seems reasonable. There's no discernible pattern there. So I think a linear model is most appropriate. Okay, does the least squares regression line give us an overestimate or an underestimate for the length of the Intimidator 305? Now recall the Intimidator 305, that's the one that has duration 98 seconds and length 5,100 feet. Okay, it's number 3. The one that has duration 91 seconds, length 5,100 feet is that. And wow, the least squares regression line gives us an underestimate for the length of the Intimidator 305, because the least squares regression line predicts that this will be the length of the roller coaster. But look, this one is a much longer roller coaster. And so this is the error. So this was what we predicted. This was actual. So the least squares regression line gives us an underestimate. We can also see this from the residual plot. Recall that residual is prediction error. It's actual minus predicted. It's y minus y hat. So again, y is the actual, and y hat is predicted. The residual is positive. In fact, here's the residual. It's a whopping 1,333 feet. Now, the residual is y minus y hat, and that's greater than 0. In fact, it's 1,333. So if y minus y hat is greater than 0, that means that y is greater than y hat. In other words, the actual is greater than predicted. And if the actual is greater than the predicted, the least squares regression line gives us an underestimate. So whether you look at the original graph, the scatter plot, or the residuals, it's clear that the least squares regression line gives you an underestimate of the actual length of the roller coaster. Can we use the least squares regression line, y hat equals 15.46x plus 2252, to estimate the length of Steel Dragon 2000 in Nagashima Spa Land in Japan? The duration is 240 seconds, 4 whole minutes. No, 240 is far beyond the longest duration. This is an example of extrapolation, making a prediction beyond your data. Extrapolation is okay. For example, it would be okay to predict the duration, to predict the length of a roller coaster that has duration maybe 210, or certainly that has duration 150, so something around here. But man, if you're picking, or if you're trying to predict the length of a roller coaster that has duration 240, that's just way beyond all of these data points. And that's, extrapolation's okay, but be careful if you're making predictions that are way beyond the data. And in this case, 240 is way beyond the other data points, so I wouldn't do it. What would happen to the least squares regression line if we included Steel Dragon 2000 in the data set? Well, the duration is 240 seconds. It turns out the length is 8,133 feet. And the graph on the next page shows what happens. Okay, here's Steel Dragon 2000. The old line's in black, and the new line is in red. Notice what happened to the line. This new point pulled the least squares regression line towards it. Because the x value of the point is far from the mean of the x values, again, this x value is about 8,000, and the mean of the other x values is around here. I'm sorry, the x value is 240, and the other x values have mean around 150. Because the x value of this point, namely roughly 240, is far from the mean of the x values, we say that this point has high leverage. Points with high leverage can sometimes have a significant influence on the least squares regression line and the correlation. The term high leverage is appropriate. Note that points with x values near the point are pulled towards it, and points with x values far away from the point are pushed away from it. This point is like a lever. And in case you can't see what I mean, again, the black is the original line and the red is the new line. So again, if there are any, so points on the least squares regression line that are close to it, those are pulled towards it. So here, the red line is closer here to the point than the black line is. But notice notice over here, the least squares regression line is pushed further away. So if you had a point that was even further, like if you had some point that was way up here, then your least squares regression line would be like this. I mean, that would have really high leverage. Again, points with x values that are close to it, those are pulled toward it, and points with x values that are far away from it, those are pushed away. So again, points that have x values far from the mean of the other x values, those are points with high leverage. Now, this new point had a significant influence on the correlation as well. When we included this point, the correlation went from 0.717 to 0.829. And that's going to happen, again, that can happen with points with high leverage. A point with high leverage has the potential to influence the least squares regression line, but it does not always do so. For example, if a point with high leverage is close to the least squares regression line, then omitting it will not affect the line much. So, for example, if your next point, if instead of being up here, your new point was over here, holy cow, that would be right on the least squares regression line. So forget about that red line. Your new least squares regression line would be pretty much the same as your old least squares regression line, because you're adding a point that's right on the least squares regression line. If omitting a point would have a significant impact on the least squares regression line, then we say that point is influential. This point, for example, is influential, because if we drop it, it has a significant influence on the least squares regression line. A point with high leverage can possibly be an influential point. This one is high leverage, it's an influential point. Also, a point with a large residual is an influential point. For example, what would happen to the slope of the least squares regression line and to the correlation if we included a roller coaster with duration 100 seconds and length 8,000 feet? So in other words, that's this point over here. What would happen if we added that point to the data set? Now, this is not a high leverage point. High leverage point has to have, an x value over here or an x value over here. It's got to be far away from the mean of the x values. We don't have a high leverage point, but we do have a point with a high residual. Look at this. the difference between the actual and the predicted is pretty high. In this case, this point would decrease the correlation, and thus decrease the slope of the least squares regression line. And here's why it would decrease the correlation. When correlation is big, that means that as x increases, y increases. But notice, here we have a low x value and a high y value. That means it's going to decrease the correlation. If, on the other hand, we added a point way up here, that would increase the correlation because that has high x and high y. But low x and high y, that decreases the correlation. In fact, if you were to draw the new correlation, it looks something like this. So it would decrease the correlation, and that always decreases the slope of the least squares regression line. By the way, the fastest roller coaster in the world is Formula Rossa at Ferrari World in the United Arab Emirates. Its top speed is 149 miles an hour. In fact, riders go from 0 to 149 miles an hour in 5 seconds. My advice to you, don't ride this after you eat a big lunch.